Hey guys, we're going to talk about the Bernoulli equation, and I love the Bernoulli equation. It's foundational to fluid mechanics. So it was attributed to Daniel Bernoulli in the late 1700s. He derived it from conservation of momentum applied to a streamline. So what's a streamline? A streamline is a line that is everywhere tangent to the local velocity vector field. That's a lot. So let's go over this. Imagine you have an airfoil and you've got flow going over the airfoil. So I've drawn these velocity vectors, as you can see. If I draw a line everywhere tangent to those, it would look something like that. We call that the streamline. In fact, technically, what you think of as a streamline is actually a streak line or a path line. If you blow smoke in a wind tunnel, what it streaks out is the streak line. But for steady flow, the streamline, the path line, and the streak line are all the same. So we'll just not get into too much detail there. All right, so if I apply conservation of momentum along the streamline, say at two locations, at location 1, and here some little volume is translated downstream to location 2. If I sum up all of the forces acting at each one of those, I'll find that these are all constant. So you recall that the static pressure plus the dynamic pressure plus the hydrostatic pressure at location 1 has to equal the static, dynamic, hydrostatic at location 2. And in fact, they're always constant. And I love to think of this kind of like in terms of money. If you spend a lot at pressure at location 1, you don't have much left over to spend it on kinetic energy or potential energy and so forth. So as the flow moves along the streamline, it exchanges potential energy with kinetic energy with elastic energy, which is really what pressure is. So those are each constant, and it's in fact constant everywhere on the streamline. So let's go over each term. That's the first term is the static pressure. That really should be under this P1 here. That's the static pressure. That's your classic thermodynamic pressure. Here's the dynamic pressure, 1/2 rho v squared. And here's the hydrostatic pressure. And this alpha sometimes is listed in various textbooks and so forth. It's a correction to the integration that we had to do when we assumed inviscid flow, much like what we did in the momentum in the previous lecture. It's sometimes tossed in there to correct for that integration being nonlinear because of the velocity squared term. Anyway, the sum of the static and dynamic pressure is called the stagnation pressure, or sometimes the total pressure. All right, so to get this equation, we had to run through all of these assumptions that the pressure includes the hydrostatic variations. The flow is steady and compressible, inviscid, no heat transfer, and it is reversible, meaning no friction. All right, and it's worth noting again that this is conservation of momentum. Even though it looks a lot like conservation of energy, it's momentum applied to a streamline. So this stagnation pressure that I talked about, let's talk about that for a second. If I go and I attach a pedostatic tube to a wind tunnel, I'm assuming that when I measure that pressure, I'm not disturbing the flow field at all. I'm not changing its elevation or changing its velocity. So when I put a hydrostatic tube, a manometer into that flow, I'm directly measuring the static pressure. If I bring that tube up and I turn it and I stop the flow field, what I'm doing is I'm forcing all of the kinetic energy to zero. I'm assuming that the little atoms that go right into that manometer come to rest, they give up their kinetic energy, and it goes into the potential energy, the static pressure. So it can't change elevation, so it has to increase the static pressure. So that's why the velocity is 0, and the static pressure is then the sum of the stagnation pressure is then the sum of the static and dynamic pressure. And then a complete pedostatic tube, we would connect this other half to the static port so that we could then measure the difference between the stagnation and the static, which would then just be the dynamic pressure. So that's how we would get to the dynamic pressure. So we got our static pressure, our dynamic pressure, our hydrostatic pressure, and the sum of those is the stagnation pressure. So hopefully that all comes back to you. Let's do a quick example. Here we have a little Venturi tube. It has a large area at the inlet of 3 centimeters squared, and then a slight neck, 2 centimeters squared. It's drawing atmospheric air in at a volumetric flow rate of 0.3 meters cubed per second. What's the pressure in the throat? Sounds like a simple Bernoulli problem to me. So there's the Bernoulli equation. We pick a streamline. I'll just go ahead and pick this streamline here. And that would mean that Z1 and Z2 are the same, or in the coordinate system, that saying R isn't changing along that streamline. So that means our Bernoulli equation simplifies to just that the pressure at 2 is equal to the pressure at 1 plus the dynamic pressure at 1 minus the dynamic pressure at 2. Well, I could calculate the velocity at 1, but I don't know the velocity at 2 here. So I'm going to need another equation. I have two unknowns. I know the pressure at 1 is atmospheric pressure. I don't know the velocity at 2, nor do I know the pressure at 2. So two unknowns, one equation. That leads me to believe I need another equation. So let's throw in conservation of mass. For all the assumptions that I needed to use the Bernoulli equation, steady, inviscid, plug, flow, that reduces the conservation of mass to this simple expression. And for one inlet, one outlet, I get rho VA in is equal to rho VA out. So I can rearrange this to solve for the velocity. If I know that the area at 1 is larger than the area at 2, then just through basic conservation of mass principles, I would imagine that the velocity at 1 is then smaller at the velocity at 2. If it comes down and necks down and the flow can't compress, then it must increase in velocity to keep the mass flux constant, right? So you can see that just with these simple terms here. Likewise, if the elevation isn't changing of the flow, if the velocity comes in and it increases from 1 to 2, it means that the pressure must decrease, right? So I'm assuming that if the velocity at 2 is larger than the velocity at 1, then I know that the pressure at 1 must be larger than the pressure at 2. All right, so I can rearrange this momentum equation to get that the velocity at location 2 is 10 meters a second. Then I can put that into my Bernoulli equation and just turn the crank, and I get that the difference in pressure is just this difference between the atmospheric pressure and 33 pascals. So my answer is minus 33 pascals gauge. And I look up here and I don't see minus 33 pascals gauge. So which one of them is it? Well, it's not that one. That's plus 33 pascals gauge. I recall that I can change this to a vacuum pressure by changing the sign. And so that would be my answer. Not that. That's 33 pascals above atmospheric pressure. That's 33 pascals. That's absolute pressure. That's just above absolute vacuum. So that's not the answer. And then this is just crazy talk. There's no such thing as minus 33 pascals below absolute zero. All right, let's do this water jet problem. So this is a classic one as well. I've got a fountain where the water is exiting through a nozzle with a 1 inch squared. What's the initial velocity? So in this one, I'm thinking that, you have this fountain and you're shooting water out of the nozzle. It has lots of kinetic energy initially, and it flies up, giving up all of its kinetic energy to potential energy until it comes to rest, and then it would fall back down, right? So at the very top, all the flow has been converted to potential energy. So the assumptions would be that the change in elevation, if I pick a streamline that's along here and I say this is location 1, and at the very top is location 2, then the change from 2 to 1 is 10 meters per second. And I know that at the top, the velocity is 0. It's given up its kinetic energy. And I'm going to use the free jet assumption. Right when the water exits the nozzle, right then, the water relaxes and comes to equilibrium with its surroundings. So that's the free jet assumption. And it means then that the pressure is constant all the way along the jet, right? That's pretty cool. So P1 is equal to P2, and we could work in gauge or absolute pressure there. And so if I plug all of those assumptions into the Bernoulli equation, velocity 2 goes to 0, and the pressures are constant and equal, so they cancel. I can rearrange to get this, that the velocity at 1 is equal to the square root of the potential energy there, and 25.3, so it looks like it's closest to this guy right there. What if I change this question? What if the question would be, what is the approximate pressure at the base necessary to drive this flow. So if you were picking a pump, the pump would jack the pressure up. How much pressure would you need to get 10 feet fountain? Well, what I could do is I could assume that just below the nozzle is some large tank, and the water is pressurized in that large tank. And I think I could get at it that way. So I'll make the large tank assumption that the velocity is 0 in the tank, and then it squirts out, exchanging its elastic energy or pressure for kinetic energy and then to potential energy. So that's what we're going to do. We could easily estimate the pressure if we assume it to be stagnation pressure. This would be akin to a large pressure with a hole in it and the water shooting up. So I'm assuming that both velocity at the inside this tank and at the top of the jet is 0. And so then I would just get that the pressure difference is equal to the elevation difference, blah, blah, blah. Crank it out, and it's about 4.3 psi. Is this gauge pressure or absolute pressure? The answer is it's really either, right? It's a pressure difference, so it's not really gauge or absolute. It's like saying a 10-degree change in Celsius is the same as a 10-degree change in Kelvin, of course. So it only becomes one or the other if when I pick an individual pressure measurement, then it determines what the other pressure measurement is. All right, hope you enjoyed it. Do some practice problems.